So when we looked at algorithms on weighted graphs for shortest paths and for minimum cost spanning trees, we had to use some data structures in order to make the updates efficient. So at the time we assumed that these data structures were available and we went ahead and did an analysis of these algorithms. Now let's go back and look at these data structures. So we begin with the union find data structure, which is used in Kruskal's algorithm for the minimum cost spanning tree. So recall how Kruskal's algorithm works. We arrange the edges in ascending order of the cost and we process the edges in this order. So each edge we pick up, if it doesn't create a cycle, we add it to the tree. And we observe that not creating a cycle is the same as keeping track of the components that we have so far and checking that the endpoints lie in different components. So the edge u, v can be added if u and v currently are not connected, they are not in the same component. Now, as a result of adding this edge, the two components do get connected, so we have to merge the two components. So the bottleneck in implementing Kruskal's algorithm efficiently is to keep track of this collection of components in order to check which component a vertex belongs to and to merge two components whenever we add an edge connecting them. So formally, the problem that we are trying to solve is to maintain a partition of a set and update this partition. Right? So by a partition, we mean that we have a set S and it's broken up into some disjoint subsets. So these subsets don't overlap, right? And every element belongs to one of these things. So there may be some which have more than one element, but each element is assigned to exactly one partition, right? And we call these partitions also components. So in Kruskal's algorithm and other applications, very often we start with a partition in which every element is on its own. So we never have maybe two elements in a partition. So we will call this setting up this data structure. So we will call it union find because the two operations we actually support on this data structure are called find. So this is a query operation. It says given an element S, right, let me know which component it belongs to currently. So this is an update which it doesn't update the data structure, it just queries the data structure and tells us in which of these partitions does S currently lie. And then we have an update which allows us to take two partitions, right? So maybe we take these two partitions and say now combine them into a single partition. So we call this union, right? So there is a union operation which merges partitions together, and there is a find operation which has to keep track of which partition a set belongs to, because an element belongs to, because over time the partition it belonged to originally would have got merged with other partitions. And because of these two operations, union and find, we call this a union find data structure. Data structure which supports these two operations efficiently. And the initialization of this union find is an operation which takes a set and breaks it up into, if it has n elements, breaks it up into n components, each containing one element. So the first issue that we have to deal with is about the names of the components. What do we call these components? A simple solution we will find is to just use the elements of the set itself as the names. Right? So it doesn't really matter what names we give. We just need to be able to check periodically whether S and T or U and V belong to the same component. So we just need to know whether find of U is equal to find of V. Right? So the exact choice of how we label find of U and find of V doesn't matter so long as we can check whether two labels are the same or they're different. But rather than manufacture a set of labels out of thin air, we will actually choose the labels to be the set elements themselves. So initially we said every element lies in a single partition. So supposing I have a set consisting of STU, then I would initially have three partitions, one containing S, one containing T, one containing U. Now the question is what do we call these partitions? Well, we'll just call them the same thing. We'll call this the partition S, we'll call this the partition T, and we'll call this the partition U. Okay, so sometimes the names of the elements will refer to names of partitions, sometimes they will refer to the names of the elements themselves. Now what happens when we merge, for example, supposing we merge these two partitions, right? Then the label has to be the same. So the element doesn't change, but maybe we might take the set, the label U and make it T. So now both element U and element T belong to the partition labeled T, right? So we just use as a set of labels the names of the elements themselves. So in particular, if we are dealing with graphs, the elements are the vertices typically. And we've already had a convention that we have n vertices in our set, we call them 1 to n. So our set of elements is 1 to n, and so is our set of components. Okay? So what we will do now is the easiest way to keep track of this is to set up an array, right? So we have an array which we will call component. And what will this array say? Well, this will say that for each of the vertices or nodes 1 to n, which component it belongs to, right? So initially we said each component will contain exactly one vertex, so we can just have a vertex n or vertex I in component I for every n. Okay. In general, after some time these might change, so this might have gone to component 3, this might have gone to component 7, and so on, right? So over time the component that a node belongs to changes because of the union operations. So then when we have find, we will just return the current value of component of I. And for union, all we have to do is we have to check and make all the components, both the components k and k prime have the same label. So rather than invent a new label, we will choose either k or k prime. In this case, we choose k prime. So what we will do is we will go through, and wherever we see a k, we will replace it by k prime. Right? So we will systematically replace every entry of the form k in this array to k prime. So after this, all component values which used to be k are now k prime. All which were k prime remain k prime. So effectively, the two components have been merged. So this is a very simple implementation of union find. So let's try and understand why this is not a very good implementation from a complexity point of view. So clearly, in order to make the initial things, we have to scan the array once, and then we just have to initialize component of I to be the value I. So this takes order n time. So this is fine. Similarly, finding an element is efficient. We just have to look up the ith element in the array, and remember that in an array accessing any element takes constant time. So this is an efficient operation, it takes constant time. On the other hand, union is a problem, because the way we have described union, we have to go through every node, check if its component is k, and if it is component k, if component of I is k, we have to update it to k prime. Right? So regardless of what the components k and k prime currently look like, we will have to scan all the elements and update those which are k to k prime. So this will take order n time for just one union operation, which is independent of the size of k and k prime as current partition sets. Right? So if we do a sequence of m such operations, then this will be order m times n, right? And if it is n such operations, it will be n square. Right? So a sequence of m operations, each of them will take order n time, and we would like to improve on this. So basically we want to see if we can improve on the speed of the union operation. So let's make a slightly more elaborate representation. So we keep this array component as before, which tells us for each vertex I which component it belongs to. And the components as before are initially labeled 1 to n, and the names are drawn from the same set. So basically 1 to n are the vertices, 1 to n are also names of components, and initially the component of I is, the vertex I is in component I. Now we have a separate array of lists, right? So for each component that we currently have, we keep a list. So initially the list says that the component 1 consists of the vertex 1, the component 2 consists of the vertex 2, and so on. Okay? But over a period of time, we could have a situation where the component 4 consists of vertexes 1, 2, 4, and 7. Right? So for each component, we have the list of vertices that it belongs to. And we will also separately keep track of the size. So we'll say that the size of this component is also 4, where the size of this component is 1. Okay? So we have two auxiliary things. We keep for each component k the list of its members explicitly, and we also keep the size of this list. So we know exactly how big each component is at any given time. Initially, of course, the size is 1. Right? So when we do a make union find, we set component I equal to I as before. Then we initialize that the members of the list I are component I are just the list containing I itself, and the size of each component is 1. Now find is exactly the same as before. We just have to look at component and return the value that component I points to. Union is also similar to before. Okay? So what we need to do is we need to set everything that is pointing to k to point to k prime instead. So every entry in component which says k should become k prime, but now we can do this by just looking at members. So we don't have to scan all the elements 1 to n. We can look up every element that appears in members of k and update its value to k prime. Right? So this is one saving. We no longer have to go through 1 to n. We only have to look at exactly the members which belong to the set K. Then of course we need to update these new things. So members of K now become members of K prime. So we will merge these two lists. Now remember that these two lists are in sorted order. We can assume that they're always kept in ascending order of the names of the elements. So merging two sorted lists as we did in merge sort takes time proportional to the length of the final list. So this will be a linear time thing in proportional to the size of the components K and K prime. Finally, we now have one new component which subsumes the earlier two, so its size is exactly the sum of the previous two. Because these are partitions, no element was repeated, so every element that joins the partition is a new one. So size of K prime is exactly size of K plus the old size of K prime. So why do we get some benefit from this? So the first thing, as we said, is updating a component is now proportional to its size, right? So updating a component takes order size of K steps. It doesn't take order n steps. We don't have to go through every vertex from 1 to n. We can explicitly look up those elements mentioned in members of K and only update those values. But size of K actually plays a much more important role. What we can do now is we can determine whether to relabel K as K prime or K prime as K. Remember, we have a choice. When we merge K and K prime, all the elements are going to become part of the same component. So the new component will be either called K or it will be called K prime. So which one should we choose? So the strategy that we are going to do is to keep the name of the larger one. Right? So if the size of K is smaller than the size of K prime, that means K prime currently has more members than K. Then we will keep K prime as the name of the final set. So we will replace all the K's as K prime. And symmetrically, if size of K is bigger than size of K prime, we will replace all the K primes as K. Right? So the smaller set changes its name, the bigger set keeps its name. So this doesn't give us any benefit in the worst case of an individual union operation. Supposing we have size of K and size of K prime roughly the size of half. So if we have built up two components which are roughly half the size of the overall set, then whether we merge K or K prime into the other set, we have to update about half the values. So this is an order n operation, right? So earlier we had said that without doing anything fancy, we will scan all the vertices and the worst case for, and in fact every case of update will take us order n time. Now it says that there is a worst case where we cannot avoid taking order n time. So n by 2 is order n. So therefore, what have we gained? Okay. So what we have gained cannot be really accounted for in terms of individual merge operations. We have to look at the cumulative effect of a bunch of merges. So we need to do what is more careful accounting. We have to account for the operations. So remember, we did some careful accounting when we did things like when we used adjacency lists and breadth first search. We said, okay, across all the loops we will see each edge exactly twice. Therefore, across all the loops we take order m time. So we need to do a similar kind of careful accounting across not one merge but all the merges that take place. So the effect of merging the smaller set into the bigger set is that if I look at an individual element, the component, if it changes its label, right, if the component is currently K and it becomes K prime, then the new set is at least twice as big as the old set. Right? So supposing I had a set K and an element S in it, and I had another set K prime, okay, and then I decide to merge these into a single set. Now, by assumption, if the new set continues to be called K prime, that means that K was less than K prime, okay, or you could even say less than equal to, it doesn't really matter. So since K is smaller than K prime, what this means is that if I look at K plus K, which will be double the size of the old set, this will be less than or equal to K plus K prime just by substituting, and therefore this is going to be, so this is the size of the new set, right? K plus K prime is the size of the new set I construct, and it's going to be at least twice the size of the old set. Therefore, whenever the name of the set labeling the component of an element changes, the new set it belongs to is at least double the size. So now let's look at some sequence of M union operations starting from the initial condition when I have all elements in separate partitions. So what can happen in each operation? Perhaps I combine two elements. Right? Now if the next time if I combine these two, then I totally in two operations I have only affected three elements. So in the worst case, if I start doing this separately each time, in one operation I affect two, in another operation I affect two more, and so on. So after a sequence of m operations, at most two m elements have had their status changed from the initial condition when they were pointing to a component consisting of only themselves. Okay, so that means only two m elements have ever been affected by my union operations. That means a component cannot have got larger than 2m, right? Because in order to get into a component, something must change. Only 2m elements are allowed to have any change applied to them at all, right? So the size of any component after m union operations at most 2m. But how does the size grow? It goes 1, 2, 4, because it keeps doubling up to m, right? So after log m steps, okay, if I double 1 log m times, I will get m. So therefore, a component S can be relabeled, a fixed element S can be relabeled at most log m times, right? So because we have this doubling, the number of times that a set can be, an element can move into a new set is restricted, because each time it moves, the size of its component doubles, and there's a limit on the largest component it can belong to. So therefore, if we look at the sum total of m union operations, we know that 2m, so order m elements have had their component updated, and each has been updated at most log m times, right? And remember now that when we are updating elements, we don't touch any element which is not updated. It's not the old setup where we have to scan all the nodes 1 to n in order to decide which ones to update. Because we have this list members, okay, when we want to update the component k, we exactly update only those components. So we only touch the components which change. So m elements change log m times. So totally we have m log m steps of change. Right? So if we do m union operations, we take m log. It is not that each one takes m log m time directly, but the cumulative total of m union operations is only m log m. Right? So this we can average out in a way to say that therefore, since there were m operations and the total is m log m, even though some were small, some were big, on an average they take log m operations. So this is a different kind of analysis. It's not quite the analysis we did for example, for the adjacency list in BFS, where we just added up everything across the whole thing. Here also we are adding, but we are also kind of pointing backwards and saying, okay, now there are totally so many operations, and the total time taken across all these operations is so much. So we divide and we give each a share of the total cost. So though it is not the case that every single operation takes log m time, we can kind of believe that this gives us a log m implementation of the union operation. Right? So this kind of analysis is called amortized complexity. So this is a term which actually comes from accounting and from financial things, where you have certain costs which, for example, you might have in order to run a business, you might have to set up something, right? You might have to set up an office and all that. So now if you cannot say that my cost on day one was a lot because I have to do a lot of work to set up the office, and therefore day one was expensive. What you have to do is look at the total lifetime of your operation and say, okay, this cost is divided across the entire thing, so is it worth it? Right? That is called amortization, where you kind of take some fixed cost of a fixed piece of equipment or asset or work and divide it across the entire lifespan when it's going to be used. So in the same way here, we are kind of doing an amortized analysis. We are counting across all the m union operations how much time it takes, and then working out that each one takes roughly log n time. So how do we use this union find data structure in Kruskal's algorithm? So remember, in Kruskal's algorithm, we initially sort the edges. So we have E1 to EM in ascending order of cost. Now we begin with a trivial partition. So we do a make union find of our set of vertices. So each vertex j is labeled j. So we have exactly n partitions, one containing each vertex. Now we need to add the current edge we are looking at, provided it doesn't create a cycle. This is the same as saying that its endpoints must be in different components. This is the same as saying that if I do find of u and find of v for an edge uv, right, find of u is not equal to find of v. And if find of u is not equal to find of v, then I need to do a merge. So I need to do union of these two components. I can get their component names by using find u and find v. So this will be some k in general, the component containing u. This will be k prime, the component containing v. And I do a union of those, and I've got a new component which contains both u and v. So since the tree has only n minus 1 edges, we will only add n minus 1 edges out of the total set to form the spanning tree. So therefore we have order n union operations to perform overall, and we know therefore for any m operations we said it will take m log m. So for n operations we have an overall amortized cost of n log n, right? So the maintaining the partitions and adding them and all that takes n log n. Now initially we had to sort the edges, so that takes m log m, but as we discussed when we actually looked at Kruskal in detail, since m is at most n squared, we know that log m is 2 log n at most. Okay, so at the level of orders of magnitude, log m and log n are the same, so we can look at m log n, m as the same as m log n. Right? So the total cost now comes out to m log m log n plus n log n, so we get m plus n log n. And if you remember the complexity that we claimed for Prim's algorithm and also actually for Dijkstra's algorithm, which is similar to Prim's in structure using heaps, we claimed that those were both of the type m plus n log n if we used a heap to do the minimum distance calculation. So therefore Kruskal's algorithm with a union find data structure essentially has the same complexity as Prim's algorithm using heaps. So to summarize, what we have seen is that we can implement union find using an array to keep track of components, an array of lists to name the vertices in each component, and another array to keep track of the size of each component. With this, the initialization step of making the union find data structure of disjoint individual element partitions is order n. Find takes constant time. The amortized complexity for a sequence of m operations is m log n. So we can think of each union operation as taking log m time for over a sequence of any such m operations starting from the initial thing.